This video clip is about infrared spectroscopy. Bit of background to infrared spectroscopy first is that some molecules absorb infrared light, carbon dioxide, water and methane. This leads to the natural greenhouse effect. We also use infrared spectroscopy to identify bonds in organic molecules. How do bonds absorb energy? The infrared light hits the bonds and the bonds vibrate. They do a little wiggle, they do a little dance. So different bonds absorb slightly different energies. For example, the bond in the O in water, so the O bond H in water, absorbs an energy of 2,500 to 3,000 wave numbers. A wave number has the units centimeters to -1. That means that you can fit in 2,500 waves to 3,000 waves per centimeter. Carbon dioxide absorbs a frequency in a lower frequency range between 1680 to 1750 wave numbers, and the stretching here goes from side to side. Technically you're putting in vibrational energy into the molecules so that they absorb the energy. So in infrared spectroscopy, we can determine the types of bonds in a covalent compound. A beam of infrared radiation goes through the sample and the molecules absorb the IR at characteristic frequencies, increasing their vibrational energy as already discussed. So different bonds absorb different wavelengths, and the same bonds in different environments will also absorb different frequencies, slightly different frequencies. More coming up on that later on with OH. Strong bonds vibrate at higher frequency wave number than weaker ones. And remember that a wave number is the number of waves that would fit into 1 centimeter. That's just an overview, more coming up to explain all that. So this is a picture of how IR spectroscopy works. You have a source of infrared radiation, and the IR radiation is represented by these black and red arrows. The black and the red arrows then fire through the sample, and the sample will absorb some of those light if they absorb the right frequency, and some will pass through the sample to hit the detector, and the detector recognizes those frequencies of light that haven't been absorbed, and you will get a printout of the infrared spectrum. So this is what the different wave numbers are for the different bonds in AS chemistry. So the bonds are amines, OH, CH, OH acids, nitrile, carbonyl, CO, and CC. So you can see that these different bonds absorb different frequencies and summarized in this table. You will be given this in your exam, so you don't need to learn them. But it's useful to refer to this when you're doing some of the other questions. So find this table on your back of your periodic table or on Moodle. So this is the spectrum of ethanol, and it is a so the axes, first of all, we have wave numbers. So this is the printout given from the IR spectrum, and then we have the percentage transmittance. This is a pretty appalling diagram, I apologize. We can see that in ethanol there's a big absorbance. We actually call this a peak, even though it's a trough. A peak at around 3,300, maybe a bit lower. Sorry, it's around 3,300. That's 3,500 there, 3,000. That's a very broad peak, and there's a very sharp peak at 2,900. There's also something called the fingerprint region, which is unique for each molecule. Each organic molecule has its own unique fingerprint region below 1,500 wave numbers. So, what are these? Why are these peaks here? Well, the OH in ethanol gives this broad peak. It's broad because of hydrogen bonding, and that's seen in other molecules as well. It's not just in ethanol, but other propan 1-ol, for example, would have that broad peak due to the OH. This is a very sharp peak due to CH bonds. Next, perhaps you can start to work out the functional group in this molecule. This is a broad peak, a bit lower than the last time, around 3,000 3000 wave numbers at the center of that peak, which is the most important bit, and also there's this very important peak here. There's a sharp-ish peak at around 1700. Can you work out what it is? So this is the IR spectrum of a carboxylic acid. We can't give any more precise details than that because we haven't got the molar mass. But this is the 2500 to 3000 wave numbers. Is the OH acid broad peak again because of hydrogen bonding, and this is the sharp peak of a carbonyl, which is between 1680 to 1620. And it's very important we give a range like this. We quote the range from the back of the periodic table datasheet. Another example is, can you state the functional group here? This, for a clue, this is not an amine, it's too low for an amine. This is the important section there to consider. So there's a sharp peak. And the answer is a aldehyde, so it's C double bond O because it has a sharp peak at between 1680 to 1750. There's a sharp peak at 2850 to 3300 wave numbers. And below 1500 here is the unique fingerprint region. So what you could do is you could have a think to what are the key absorptions for these different molecules. You could have a workout of that, and the answers are as follows. Ethanol, ethanol, ethanoic acid, ethene. You could follow through here and run through about what their functional groups are. Sharp of the aldehyde, 1680 1750 because of the carbonyl group. OH alcohol 3230 to 3550, that's the important range to mention. It's a broad peak due to hydrogen bonding. And we have propanone again, like ethanol, it has a sharp peak between 1680 and 1750 because it has a carbonyl group. Propan-1-ol also has this broad peak between 3230 to 3550, similarity to ethanol. Propan-2-ol is similar as well. But what will be the difference here? What will we see in the infrared that would tell them apart? Yes, it's their fingerprint region. They would have slightly different fingerprint regions, which you can actually find in your textbook. Ethylamine, a little bit like alcohols, has a broad peak, but it's a kind of double dip. It's a double dip and it's got a broad trough, or broad peak. And finally, ethene, just a C double bond C, 1620, 1680, again a sharp peak there. So just some questions to be aware of for the fingerprint region. So it's below 1500 wave numbers. It's unique to each organic molecule, hence fingerprint region. And it's what we can do with the fingerprint region is compare it with a database of known compounds and find an exact match that confirms the identification of the compound, underlying terms of what appeared in the mark scheme before. So, question, a little bit more open question. Oxidation of ethanol to ethanol. Use your table above to determine how you'd know if all of the ethanol had been oxidized to ethanol. If you carried out the infrared spectroscopy, which peak would not be present. So what you're thinking about here is we've got ethanol to begin with, we turn it to ethanol. Which peaks in the IR would start to disappear? Have a think about that. So the answer is there'll be no absorbance between 3230 to 3550, which is the OH alcohol. There have been absorbance, however, between 1680 and 1750, which is the carbonyl functional group, in the aldehyde. So none of this, but you would see some of that. What about this question here? How would you ethanol to ethanoic acids and oxidation? Use your table of data above to determine how would you know if all of the ethanol had been oxidized to ethanoic acid if you carried out the mass spectroscopy. I don't mean that. I mean IR spectroscopy there. Well, you could use mass spectroscopy. So how would you ensure it's all been changed? Well, we wouldn't see a absorbance between 3230 to 3550 because the OH alcohol is gone. There will be a lower absorbance. Lower, I mean no wave number value range for the carboxylic acid OH, and there would also be a new carbonyl peak for the carboxylic acid functional group between 1680 and 1750. Right, some more questions to consider. Pause the screen. Moving on to answers now. So, molecule A was analysed, and it had a sharp peak between at 1750 and a broad peak at 3000 wave numbers. Which functional group does this suggest at present? Well, that is C double bond O, that is OH, and it is the alcohol. No, it's not. It is the carboxylic acid. And it has the correct molar mass to be ethanoic acid. Next we got 1750 wave numbers, but 3300. That's an OH alcohol. That is a carbonyl. So the answer is hydroxy ethanol, which looks like this. Hydroxy group ethanol. Molecule C shows geometric stereoisomerism. That's EZ isomerism. It has a peak at 1650 and a broad peak at 3300. CC double bond, OH alcohol, ethene 1,2-diol, which looks like this, and show. We don't need to worry about it being E or Z. We're just going to draw it out. I'm drawing it out as Z, of course, for zusammen.